Hello, for our machine design project, we're going to be doing wind turbine blade fatigue. Wind energy is a key player in the shift to sustainable power, but turbine blades, especially in harsh climates, often fail earlier than expected due to fatigue. Our project explores how environmental factors and design choices affect fatigue life and how we can optimize blades using better modeling and materials. Wind turbine blades act like cantilever beams, anchored at the root and bending under cyclic wind loads. Bending stresses are calculated using the formula sigma is equal to mc over I, where m is the moment at the blade root, c is the distance from the neutral axis, and I is the moment of inertia. As wind speeds increase, bending moment and stress increase dramatically, reaching up to 90 megapascals near the root at 25 meters per second, where failures often initiate.
The red area denotes the maximum deformation or stress concentration, with the tip of the blade having the highest deflection as shown in the image on the left. The image on the right shows the top and bottom faces of the wind turbine blade respectively, with the center of each face having the maximum amount of stress. To account for bending stress, tapered and twisted blades are chosen in order to minimize the effect on the blades, with twisting reducing the angle of attack. Other factors such as temperature extremes ranging from minus 15 degrees Celsius on colder days to 32 degrees Celsius during heat waves create thermal stresses that combine with wind loads and accelerate fatigue damage. Accounting for these stressors is important to accurately predict blade life and ensure long-term durability. Evaluating fatigue life under real-world conditions involves calculating the alternating and mean stresses using bending load formulas shown. Goodman diagrams are then applied to combine these stresses and predict fatigue failure using the NF formula. Environmental factors such as temperature swings and humidity lower the endurance and limit SE through correction factors, further emphasizing the need for climate resilient design. If a blade is exposed to variable conditions, Miner's rule can be used for cumulative fatigue damage.
Wake effect refers to the reduced wind speed created in the region behind the wind turbine. This generally increases the fatigue loading on the blades by 15% and decreases the power production by 10 to 20%, therefore decreasing the efficiency of the power production process. The solution to this is to increase the distance between each turbine to be outside of the region in which the wake effect would be experienced. The materials used in windmills are primarily fiberglass, which provides the best balance between affordability and fatigue resistance. However, in extreme conditions such as windmills in the sea, carbon fiber is used, which has a higher stiffness and offers a 40% better fatigue life. The graphs on the left show how fatigue life of windmills compared to other day-to-day objects. Environmental factors significantly accelerate fatigue damage. The combination of mechanical and thermal stresses emphasizes the need for strong material choices and optimized designs. Using SN curves, Goodman diagrams, and finite element analysis helps predict and improve blade durability. Future advances in composites and climate-specific designs will be key to building longer-lasting and more durable turbines. These are our sources. Thank you.